Greetings! We learned quite a bit about moment of inertia last time, and so today we're going to learn what to go do with moment of inertia. So we're going to return to energy and look at how moment of inertia fits in with rotational kinetic energy. One of the most useful things that we'll do with the moment of inertia is use it to calculate the rotational energy of an object. Rotational energy is equal to 1/2 I omega squared. This is going to be very, very similar to kinetic energy and everything like that that we've done before. I is moment of inertia, and omega is angular velocity, just like before. The units, let's make sure that the units of this make sense. What are the units of I? Well, I is always some fraction times mr squared. If you look back at that list of moments of inertia that I gave you, you'll see that it's always something times mr squared. Well, what are the units of that? The something is always some fraction, so fractions don't have units. Mass, that's going to be kilograms. Radius, that's going to be meters, and we square it. And the units of omega, angular velocity, well, that's how many radians you go through in 1 second. So the units of rotational energy, this is units, just wanting to put the brackets around everything. The units of rotational energy will be the units of that fraction, which is no units, times units of I, which is that, times units of omega squared, which is going to be that squared. So, I, kilograms, meters squared, and then we need to multiply by the units of omega, and then square those units. That'll give us radians squared over seconds squared. But remember, radians are kind of a fictitious unit that doesn't really count most of the time, unless we're dealing with an angle. And so we can drop radians out or add it in whenever we need to. So now we're going to drop it out, and we just get 1 over seconds squared when we use this squared. Okay, does this make sense? Is this the correct units for energy? Well, to remember if that's true, I'm just going to write, okay, what was gravitational potential energy again? Well, that's just mgh. Units of m, kilograms, units of g, meters per second squared, units of h, another units of meters. Let's see, kilograms, meters squared per second squared. Yeah, look, the units of rotational energy are actually energy, same as the units of any other kind of energy. So this works. We have shown that the units of this thing are actually energy. And this is going to be how we calculate the rotational energy of an object. Now for an example of how to use rotational energy in a problem. I give you on slide 15 an example. Does a rotating tire have more kinetic energy or more rotational energy, rotational kinetic energy? So rotating tire. Does it have more kinetic energy or rotational kinetic energy? I give you some units, some constants to use with this. I say that the radius of the tire is 0.3 meters. The mass of the tire is 20 kilograms. The tire can be expressed as a solid cylinder, so I is equal to 1/2 mr squared for a solid cylinder. And that kind of makes sense for a tire. If a tire is shaped like this, well, that's a pretty solid cylinder right there. I say that the velocity is 30 meters per second. So we're finding if the tire has more rotational kinetic or kinetic when it's going at 30 meters per second. And yeah, we need to figure out rotational energy versus kinetic energy. Which one is going to be greater? Let's start with just calculating them. Kinetic energy. Well, that's just 1/2 mv squared. So we can get our calculator involved in this. 1/2 times the mass, 20 kilograms times the velocity, 30 meters per second, squared. That gets us 9,000 joules. Okay? Well, let's do it again for the rotational energy, which the equation that we had from before, 1/2 I omega squared, 1/2 I omega squared. I told you that this is a solid cylinder. You can actually just look up in the book what the equation for a solid cylinder will be, and I'll give you that on any tests and anything that you need it for. So 1/2 mr squared, this is going to be 1/2 from there, times 1/2 from I, 1/2 mr squared, times omega squared. Well, we're not given omega. None of these things are omega, so we need to figure out what omega is equal to. Omega is equal to V over R. We did that before when we started learning about what omega is just generally. That will also be something that I'll always give you on a formula sheet. You just need to know to look for it. That's the most important thing about using a formula sheet, knowing what to look for. So if we apply this in there, then we get that this is equal to 1/4 times m times r squared times v squared over r squared, plugging that in there. Those cancel out. You get 1/4 m v squared. Oh, look, that's kind of suspicious, but it's true. Kinetic energy is 1/2 mv squared, and rotational energy for a solid cylinder is 1/4 mv squared. You can already tell that this is going to be less than this just based on that fraction there. This ends up being 4,500 joules. A solid cylinder, a tire that is a solid cylinder, will, when it's rolling down the street or whatever, it will have twice as much energy locked away in kinetic energy than it will in rotational energy. Up until now, we've only been dealing with the kinetic energy of an object, trying to determine how much, say, gravitational potential has to flow into kinetic energy for it to go at a certain speed. Now we have an additional place that energy will end up going when you have something rolling somewhere. And so some energy will go into the rotational energy of an object. And there's a lot of different problems we can do with this principle here, all involving the conservation of energy. This next question is really a classic. This is from slide 18 of the lecture slides on rotations, and it's asking about the speed of a solid cylinder versus a hollow cylinder at the bottom of a ramp, just like the video from last time, just like the introductory video from the first set of videos on rotations. We rolled the solid and the hollow cylinder down the ramp, and we saw that the solid cylinder got to the bottom of the ramp before the hollow cylinder did. So let's go ahead and find the velocity of each at the bottom of the ramp. Well, let's start with the solid cylinder. I wrote that down first. What we're doing is we're finding the speed of each at the bottom of the ramp, where we have a ramp of height h. This is height h. We've got our solid cylinder and our hollow cylinder right next to each other on this ramp, and we want to know what their speeds are at the bottom of the ramp. I'm not going to give you any numbers on this. I'm only going to give you symbols on this. Okay, what kind of problem is this when we find the speed of something at the bottom of a ramp, especially when it's rotating? Well, we could do it with kinematics, but that would be awful, frankly, so let's not. Let's use energy. Delta E is equal to W. This is going to be for the solid cylinder. Is there any work being done from outside? Well, not really. You know, this could all be happening without friction slowing it down. It could all be happening without an engine trying to speed it up, so there's no outside work. So energy initial is equal to energy final. What kind of energy does it have at the beginning of the problem? I'll let you think about that for a second. Okay, it should have gravitational potential energy initially. There's no springs, there's no spring potential. It's not moving yet, and so there's no kinetic energy, and it's not rotating yet, so there's no rotational energy. What about at the end of the problem? What kinds of energy does it have at the end of the problem? Well, it's definitely moving at the end of the problem. It had to roll down the whole thing, so it's definitely moving off to the right on here. But also, it's rotating. So not only is it moving translationally, but it's also rolling as it goes, implying that I've got both kinetic energy final and rotational kinetic energy final here. Well, we can solve this. Mgh here is equal to 1/2 mv squared plus 1/2 I omega squared from there. I almost have an m in every term, but I don't quite because, well, I don't have an m right there. You see, though, that this I kind of takes the place of that m, and this omega kind of takes the place of that v. This is for a real good reason. The mass of an object is how hard it is to accelerate that object. The more massive an object, the more force it requires to accelerate an object. The greater the moment of inertia of an object, the more effort it takes to rotate that object. V is a measure of how fast that object is going. Omega is a measure of how fast that object is rotating. So in a way, just like how omega, the angular velocity, was the angular version of velocity, I, the moment of inertia, is the angular version of the mass. Mass is how difficult it is to accelerate something linearly, and I is how difficult it is to rotate, to spin something, to move something at an angle, to rotate something. Well, mgh is equal to 1/2 mv squared plus 1/2 times I. Well, this is my solid cylinder, and eventually you'll probably end up accidentally memorizing these, but the moment of inertia for a solid cylinder is 1/2 mr squared, and then we have our omega squared, and now we do have a mass in every term, so I can cancel out all those masses by dividing both sides by mass. I get gh is equal to 1/2 v squared plus 1/2 times 1/2 times r squared omega squared. Remember, omega is v over r, so I get r squared v squared over r squared. Those cancel, and so now I have gh is equal to 1/2 v squared plus 1/4 v squared. Gh is equal to, okay, now please tell me that you can do that right there. This is if you can do this algebra, I'm okay with that. If you cannot do that, then there's definitely something wrong. So this had better be 3/4 v squared. Now we can solve for v. V is going to be the square root of 4/3 gh. The solid cylinder will be moving at a velocity of 4/3 gh, square root of 4/3 gh at the bottom of the ramp. Now, what about the hollow cylinder? Let's do this again for that hollow cylinder. We've got the exact same setup. We've got a height h. We've got our hollow cylinder. It's going to come down the ramp. At this point, it's going to have some velocity, and we need to figure out what that velocity is. Delta E is equal to W, but just like last time, there's no work being done, so energy initial is equal to energy final. The initial energy is going to be the initial gravitational potential, which will equal the final energy the kinetic energy final plus the rotational energy final, just like last time. Therefore, mgh will be 1/2 mv squared plus 1/2 I omega squared. mgh is equal to 1/2 mv squared plus 1/2 times I for the moment of inertia for a hollow cylinder is just mr squared, no fraction in front of it, times omega squared. The m's cancel again, leaving us with gh is equal to 1/2 v squared plus 1/2, what was omega? Omega is v over r, so this is going to be r squared times v squared over r squared. Again, those cancel. We come up here. gh is equal to 1/2 v squared plus 1/2 v squared. Therefore, gh is equal to just v squared. And v is equal to the square root of gh for a hollow cylinder. Compare this to the solid cylinder. For the hollow, the final speed is the square root of gh. For the solid cylinder, it's the square root of 4/3 times gh. The difference is this square root of 4/3 factor in the solid cylinder that's making it go slightly faster at the bottom of the ramp. And that's, why is that though? Why is that? We see, looking at this earlier part of the work, that in the solid cylinder, we get this extra factor of 1/2 going on. That extra factor of 1/2 is in the rotational energy. That means, and there's each have this first factor of 1/2, but the hollow cylinder does not have a second factor of 1/2, reducing it by a factor of 1/2. The solid cylinder does. That means that less energy, half as much energy, will be going into the rotational energy. Half as much of the total will be going into the rotational energy of the solid cylinder. That means that if half as much is going in here, then that half that should have gone in here otherwise would go into the kinetic energy. If you have less room for rotational energy because of that 1/2 there, then that energy has to go somewhere. It's all coming from here, and so it has to go somewhere. So it'll go to the kinetic energy, meaning the object will be moving faster. You are storing energy in rotational energy right there. If you want your object to have a lot of kinetic energy, you don't want to store very much in rotational energy. You don't want to store any more than you absolutely have to in rotational energy. So by having a shape that has a smaller moment of inertia, you can guarantee that you will store less energy as rotational energy, giving you more energy that you can store as kinetic energy, allowing you to go faster. That is fundamentally why the solid cylinder will beat the hollow cylinder down the ramp. I have one more example for you from the lecture slides. This is slide 20, about finding the moment of inertia for a cylinder using calculus. Let's draw out a cylinder. Here is a cylinder. We're not given any kind of variables for this, so I'm just going to say that the radius of the cylinder is r. I'm going to say the length of the cylinder is L. I'm going to say the mass of the cylinder is m, and its density is rho. That shape right there is a rho, Greek letter for density. The equation for moment of inertia, in general, the integral form is moment of inertia is the integral of r squared dm, as we showed. And, well, we need to take this integral. Trouble is, I don't know what this dm is or how it relates to r. I guess I do know that the moment of inertia has to be judged starting at 0 and ending at r. If we integrate this over a series of concentric shells, maybe that is how we can start on this. So 0 to r squared dm. Let's try to figure out what dm could be. dm is going to be the infinitesimal mass of one of these shells. So if we take this shell and just kind of highlight it going through this shell there is going to have some mass. That mass should be the density of the object times some differential volume of that shell. This shell is going to have a very, very, very small volume because this is infinitesimals. And so you take the very, very small volume of that times the density of the whole thing, and that should give you dm. Well, what is the volume of that shell? We can think about that by imagining this shell in there with several layers under it and several layers over it, and taking that layer, that shell layer, and unfolding it like that. If we do that, then we can just say, oh, well, that layer, that shell, is just going to be something like this after it's been unrolled. This thickness here, that thickness there, is going to be dr, an infinitesimal change in radius. That's that right there. This and that are dr, an infinitesimal increase in radius of this cylinder. The length here should be L, because that's the length there. What do you think that this width is going to be? I'll give you a second to think about that. Well, that width right there should be whatever this little r is, that's the layer that we're looking at, times 2 pi, right? Because that's going to be the circumference of that layer, 2 pi r. Therefore, dv should just be the length times the width times the height. Length, width, height. So this is going to be L 2 pi r dr. We can plug that dm back in there, getting us that I is equal to the integral from 0 to r of r squared times rho L 2 pi r dr. Let's clean this up and take out everything that is not dependent on r. So it's going to be rho L 2 and pi. So 2 pi rho L integral 0 to r of r cubed dr. R cubed dr. 2 pi rho L integral from 0 to r of r cubed dr. Oh, that's not an equal sign, sorry. That's going to be 1/4 times r to the 4th. And so we get that I is equal to 1/2 times pi rho L r to the 4th. We can also remember that m, the mass of the whole thing, should be rho times the volume, which is going to be rho times the volume of this is going to be the area of the end cap times L. So the area of the end cap is pi r squared. Oh, and this is a capital R times L. And can we figure out what to do with that over here? Well, if I take out those things, I get, let's see, 1/2. I want to take out a pi, a rho, an L, and an R squared. So I keep the 1/2 there. I need to take out a pi, take out a rho, take out an L, and take out an R squared. That's going to leave me with R squared times all this stuff. Rho, pi, R, L, R squared, L. And we can see, okay, if I have the 1/2, I've got the pi, I've got the rho, I've got the L, and I've got an r squared, leaving an r to the 4th right there. But this is the mass of the object. Therefore, I is going to equal 1/2 times the mass times the radius squared. Exactly what the book says. This is the proof that the moment of inertia of a cylinder is equal to 1/2 mr squared. That's where that 1/2 factor comes from. If you do this integral on any other kind of shape, you'll generally get the same kind of thing. You'll generally go through the same steps, except that that fraction right here will change depending on what happened around in this kind of area. So be on the lookout for that. But that's how you solve for the moment of inertia of an arbitrary object.